All right, so this is Mr. Smith here. This is Algebra 2, Section 5.7, the Fundamental Theorem of Algebra. Now, this is the class called Algebra. And this section is about the fundamental theorem. So anytime a teacher says, this is going to be the fundamental idea of the entire class, you should pay attention. Not that you shouldn't pay attention all the time, but with a little bit more dedication in this moment. So, fundamental theorem of algebra. We're going to jump right to it. And so, I'm actually going to glaze over the theorem and build to the corollary. So, corollary follows from a theorem. And the theorem, that, as the textbook presents it, isn't that useful. But I'll walk you through it presently. So the fundamental theorem of algebra, as presented by the textbook, says if we have a polynomial of degree n, that means it's a cubic polynomial, x cubed minus 3x squared plus 2x. It's a fourth degree polynomial, x to the fourth plus 2x squared minus x plus 7, right? It's just some polynomial. Then the equation has at least one solution in the set of complex numbers. And remember that the set of complex numbers includes every number that you know. Okay, so it's a real number that's in the complex numbers. It's an imaginary number that's also in the complex number system. Okay, so this theorem basically says if you give me a polynomial, it must have at least one solution. It's just not really useful. So we jump to the corollary, and this corollary is what I've been emphasizing actually since we began the chapter, and it is this. If we have a polynomial, and this is really the thing you need to write. I wouldn't worry about the theorem. It is the corollary that matters. If we have a polynomial of degree n, then the equation has exactly n solutions. This is it. The equation has exactly n solutions. Provided two things. Number one, provided we talk about complex numbers. Okay? So it has exactly n solutions, either that are real numbers or imaginary numbers. And provided this, that if we have a solution that's repeated twice, we count it as two solutions. If we have a solution that's repeated 3 times, we count it as three solutions. Even though it's the same number, it's just a means of counting. And we usually refer to this as multiplicity. Multiplicity. Yeah. Okay. That being said, this basically is the rationale or the reason that allows us to say, if I have a cubic polynomial, how many solutions does it have? It has exactly 3. Okay, what is the mechanism that allows us to say it? It is basically the fundamental theorem of algebra. Okay. While we're picking up theorems, I'm going to show you one more. Okay. So if you will join me here, and this is the complex conjugates theorem. Complex conjugates theorem. It says this. If I have a polynomial function with real coefficients, and a plus bi is one of the solutions. In this case, they say it's at 0, but it's one of the solutions. If I know that a plus bi is one of the solutions, then there also must be another solution that is a minus bi. That is, complex solutions always occur as pairs. Complex solutions always occur as pairs. So for instance, if I told you that for a given polynomial, one of the solutions is x equals -3, and one of the solutions is x equals 2 plus 4i. Well, if one of the solutions is 2 plus 4i, then this theorem tells me that there must be another solution, because complex solutions always occur in pairs. And what is the other solution? It is x equals 2 minus 4i. Right? Those are conjugates of each other. Okay? So we have two very, very important theorems that really help us to round out this chapter. Number one, the fundamental theorem of algebra, specifically the corollary, says if we have an n-degree polynomial, then it has exactly n solutions. Second important theorem, complex conjugate theorem. It says complex roots always occur as pairs. It always occurs pairs. And the pair is the conjugate. The pair is the conjugate. Okay. So let's see this in application. So here, let's look at part A. This is a cubic polynomial. How many solutions does it have? How many solutions does part A have? Cubic polynomial must have 3. Now, so there must be 3. Okay. Now the next question is, can all 3 be real? Could all 3 of the solutions be real numbers? Let me put that, and then let me put a question mark because you guys are unsure. So let me ask a different question. Can all 3 be complex? That's what I mean here with the C with the line through it. Can all 3 be complex? The answer is no, because complex roots always occur in pairs. So how could I have 3 complex roots? Right? They always have to occur in pairs, so there can't be 3. Can there be 3 real? Yes. So this is yes. And then what's another way that I could order the solutions? Is there any other? I have 3 real. Can't do 3 complex. Can I do 1 real? And then 2 complex? I have to do that. 1 real and 2 complex, and the answer is yeah. Right? I know I have to have 3, and as long as the complex ones occur as a pair, I'm fine. Okay? So this isn't telling me what the solutions are. It's just telling me how they have to occur. Okay. What about part B? How many solutions does it have? It must be 4. Could all 4 be complex? Yes, as long as they're occurring in pairs, that's fine. Could all 4 be real? Yes. Could I have 1 real and 3 complex? No. Complex roots always have to occur in pairs. Likewise, it cannot have 1 complex and 3 real. So it tells us what kind of solutions we should be looking for to know these 2 theorems. It tells us how many and whether to expect real or complex. So this now becomes the stepping point for which we entertain this problem. And this is the problem. This is it, really. I want to solve this polynomial. I want to set it equal to 0. That's what it means. Find all the zeros. So I want to set this to 0, and I want to solve that. And it looks like the warm-up problem that we did today, which those of you who are watching the video didn't do. But for those in class, right, it looks a lot like the warm-up problem, except what's missing? What don't I have? Go ahead. That's right. In the previous problem, it gave us one of the solutions. And then what do we do? That's right. Right? We divided by it. So we got one of the solutions, we fixed the notation, and then we divided by it. We don't have anything. So first of all, let's talk about what type of solutions could we expect. So how many should there be? There should be 4. They could all 4 be complex. But if they're all 4 complex, we can't solve this problem. In high school algebra, we have no means to be able to solve this problem if all 4 are complex. So that's out. Shouldn't happen. They could all 4 be real. But if all 4 of these are real, we could simply look at the graph and we get them all. It'd be very easy. Just look at the graph, all 4 come out. So that's possible, but unlikely. What is more likely is that 2 of the solutions are real, 2 of the solutions are complex. So let's go with that assumption, and I'll tell you that is true in this case. 2 of the solutions are real, and 2 of the solutions are complex. And the question then becomes, how do I get the 2 real solutions? Because once I have the real solutions, then I can divide out by them. If I have the 2 real solutions, I can divide out by them, but how do I get the 2 real solutions? Answer for us is graphing. Okay, we're going to graph the original quartic equation, and we're going to get the 2 solutions from that. Okay. Now, there is another approach, one that's to be known, even in the video. There is another approach. It is in section 5.6, and it's called the rational root theorem, and it's basically a guess and check method. The rational root theorem basically is a guess and check method to find out the real roots. In my mind, we have a very powerful tool at our disposal. It will tell us where the real roots are, so let's use that. Okay, so I'd like everyone now, at home and in class, to go ahead and graph this quartic equation. And remember that I'm expecting 2 real solutions, so that means 2 intersection points. And I'm expecting 2 complex solutions, which means I won't see those intersections. Okay, so go ahead and graph this now. If you're at home, why don't you pause the video and graph as well. All right, so we're looking at the graph. I went ahead and graphed the quartic equation on the computer, on the TI Inspire, and I found that x equals -1 and x equals 4. So we'll come back now over here, and x equals -1 and x equals 4. So that means I want to think of that as x plus 1 equals 0, and x minus 4 equals 0. And now here the fun really begins. What we're going to do is we're going to divide that 4th degree polynomial by one of our 2 factors. And it doesn't matter which one we pick first, because then whatever we get, we're going to divide that by the other factor. Okay, we're going to do 2 long divisions. The reason is because when I do the first long division, I'm going to take a 4th degree polynomial divided by a linear one. I'm going to get a cubic. I can't use the quadratic formula on something that's cubed. So then I'm going to take the cubic polynomial and divide it by the other factor, and that's going to give me a quadratic one. And now I'm going to use the quadratic formula. So hold on tight. Here we go. X to the 4th minus 7x cubed plus 13x squared plus x minus 20. And we're going to divide by x plus 1. So x to the 4th divided by x is x cubed. By the way, please remember, you must have every single one of these columns. If for some reason one of these columns isn't there, you need to leave a space for it with a 0 and then the value. X cubed times x to the 4th, x cubed times 1 plus x cubed. Subtract, changes the signs, bring down the 13x squared. Negative 8x cubed divided by x is negative 8x squared. Negative 8x squared times x, negative 8x cubed. Negative 8x times 1, negative 8x squared. Change the signs, and we add 21x squared, bring down the x. 21x squared divided by x is plus 21x. Divide 21x by x, multiply. And we get 21x squared. 21x times 1 is plus 21x. We subtract, changes the signs. Negative 20x minus 20. Negative 20 divided by x is negative 20. Negative 20 times x. And we should get 0 remainder, and we do. We get no remainder. So what we got out of that is a cubic polynomial. Literally, x plus 1 times this cubic polynomial would have given us back the original function. But unfortunately, we don't really have a good way to solve cubic polynomials, so we're going to divide again. Right, this time I'm going to take the cubic polynomial and I'm going to divide this by the other factor, x minus 4. So we have another long division to do here. So x cubed minus 8x squared plus 21x minus 20. And we're going to divide this time by the other factor. Don't divide by the x plus 1 again, because you'll get a remainder. Okay, that's not what we want to do there. All right, so we divide by the x minus 4. Now at this point I'm out of space on the board, so I'm going to erase this piece here. Here we go. X cubed divided by x is x squared. X squared times x cubed. X squared times negative 4 minus 4x squared. Subtraction changes the signs. Negative 4x squared plus 21x. Negative 4x squared divided by x is negative 4x. Negative 4x times x, negative 4x squared. Negative 4x times negative 4 is plus 16x. Subtraction changes the signs. So it gives us 5x minus 20. 5x divided by x is plus 5. And we should get no remainder back. And you'll see that we do. Get 0 for a remainder. Whew! I wish we were done. We're not, but we're close. Where do I take it from here? Go ahead. I'm going to take the quadratic formula, and we're going to use it on this quadratic. Now, does that factor? Could that factor? The answer is definitively no, without ever looking at it. And here's why. Remember that I expect two solutions to my original problem to be real, and here they are, and two solutions to be complex, and that's got to be the solutions to that quadratic. So don't waste your energy trying to factor this thing. It will not factor. If it would have factored, that would mean that there'd be 4 roots, and we would have seen all 4 of them right here. We don't see all 4 of them. They're not there. Only 2 of them are real. This piece, the quadratic, x squared minus 4x plus 5, does not factor. So we're off to the quadratic formula. X equals negative 4 plus or minus 4 squared minus 4ac all over 2a. 16 minus 20 is the square root of negative 4 over 2. This is 4 plus or minus. This would be the square root of 4 times I, but the square root of 4 is just 2. So 2i over 2. And lastly, we divide out by the 2's, and we get 2 plus or minus I. And now see the entire picture unfolding before your very eyes. Number 1, there are exactly 4 solutions. We expected there to be 4 solutions. Number 2, if there was a complex root, its conjugate was there, right? 2 plus I, 2 minus I. Number 3, looking at this bigger. What if I gave you a 5th degree polynomial? We'd have to do potentially 3 long divisions. Now there's one thing we could have done to shorten the process. I'll just mention it here. We'll take a look at it tomorrow. At this point, this is the concept. I'd love for you to take a look at one problem tonight. Obviously, these take a while. But here's the one way we could have shortened this. Instead of dividing the original polynomial, so I'm going to clear off everything at this point. Instead of dividing the original polynomial by x plus 1, and then dividing again by x minus 4, I could have divided the original polynomial by x minus 1, wow, that's not working, by x minus 1 times x plus 4. I may have the signs wrong there. Right? And so what this would do is this would give us a quadratic and now we could just do one long division instead of doing it in two pieces. It's neither here nor there. It's your choice. I assure you the process works the same. Thanks for your attention. Do not leave, except if you're watching the video, you can leave. Have a good day. Smith signing off.